Hi, I'm Alejandro González Escamilla, and this is my ID, and I'm going to show the core score for this week. My ID is A008-39233. In here I have the code. I performed the activity with both modalities, with the dashboard URDF and with my own robot in TFs and markers that I use the Puzzlebot for. I'm going to first briefly explain the one of the dashboard. I didn't change anything about the joint launch, nor the joint puff. And in the main launch, I only add the sample time as a parameter and uncomment that the teleoptis keyboard part. And also I launch another terminal to publish the auto message. From the actual code that it's in here, I added the messages that are going to be used. I believe that one was already there, just the one of the odometry. I call it odom message. These variables are to set up the sample time and the sample time for the loop to apply the numerical method, and the variables to publish with odom. Odom have the linear and angular velocity, and we're just only use the pose of x and y, the pose of theta, on the linear x and angular z that received from CMDVL topic. Those are the only ones we're going to use since we're using a non-holonomic robot. This part of the code was already there. For the callback and twist callback, we receive, as I said, these two variables from the CMDVL topic being published by the teleoptis keyboard. And now in the main, we initialize the node. We get the param, that it's a global private param. Yeah, private param. I need the boost transform, subscribe to the CMDBL topic, and start the publisher of the odometry topic. Set up the broadcasters to publish the TFs. And here is where the numerical method is being applied to get the pose of x and y using trigonometric functions for cosine and sine and the angular set. Since it's the only way where the robot can turn in the Z axis. We update the TF message, the hair stamp with the current time, the transform translation using the one calculating here, the same for Y, and we're not moving inside the robot, so that one stays as 0. And for the orientation, we have it in degrees. We need to transform into quaternions and then update it. Publish the transform and publish all the data that is required by the odometry message. There is also the position and the orientation in quaternions. And the twist, the linear x and angular set that is being published in here. That is all the code. The other thing is performed by the already provided code of the joint publisher and the URDF. I'm going to rapidly show it. Here's the robot. The odom message being published, and we can actually move it with the keyboard. The wheels. And that's it. The other one, using my own robot, it's almost the same. I have it in this package called Puzzlebot. In here, I do change more things of the launch file. I erase the part of the joint publisher to add my marker node. Since I use the sample time in both nodes, I state it as a global parameter instead of a private, sorry. And I open new terminals for the echo message and the velocities of each of the wheels. Then I got the STLs of the robot from a previous URDF I created for the Puzzlebot, but I'm not using it. I'm using the markers that are in the Puzzlebot marker.py, and in here is the kinematic model. I'm going to explain first the kinematic model, since it's almost the same as with the Dashco, with pretty different small differences. For example, the only difference in here is that I add some variables that are needed to calculate for the wheel velocity, since the separation and the radius. This is the same, and as the base link is called the same in both, we can use it with the same name. Same. And here I just stated the new other publishers that we have, that are the wheel speeds. Is the numeric method is applied the same to update for each of the transforms of phase link. It's translation and rotation. For the wheels, we use this formula to calculate the velocity of each of them with the linear velocity that we got from CMD Bell and the separation that have the wheels. From one on the other, the only difference of the formula is the sign. One it's an addition and the other one it's a subtraction. And then we publish the odometer message, just as in the other case, but also the velocities for the wheel. The difference, the other difference are in here. However, this is actually almost the same code as in the last week's activities. We just needed to add some extra variables to perform the wheel's speed calculations, to perform the numerical method, erase some things that we're not going to use anymore, such as the world transform, since right now the parent transform of the base link is the odometry stated in the other code. So I erased that. And I also simplified the part of the message, since I have a mesh from the left wheel and right wheel. However, they were the same, so I just leave it as one. This is just the marker definition, the mesh, the orientation, the color, etc. These callbacks are for receiving the velocities that were published in the other code. And now in the main, we got the global parameter. In each of the transforms. This part is just to update the markers and transforms continuously. In here, we state this part is just to initialize them, and this part is to actually update them in the while. In here, we're also initializing the publisher and subscriber. We're publishing the markers and subscribe to the wheel's velocity. And then in the numerical method approximation, we use the velocities to calculate for the angle. However, that angle is in degrees, so we need to transform into quaternions. That is stated in here, and then update each of the values so that the actual TF can rotate and then translate to the rotation of the marker, as the marker is attached to the TF. I'm going to demonstrate it. Let me arrange the terminals first, the odometry and each of the wheel's velocity. Here is the Puzzlebot on RBs. Very neat. Going to turn it. As you can see, from one turn, both wheels have the same velocity, and in the other one, it's also the same, just with different sign. If we do move like in a circle, one wheel moves slower than the other one. We change the direction of the circle. They change too. So yeah, everything is working as expected. And for example, in here, that is just straight line, and the velocity also in a straight line. That behavior can also be seen in the atom message. For example, the linear velocity here and the position. The positions of the wheels. That will actually be it. Thank you.